right, good evening, folks. Hi, and welcome to Flandrau Science Center and Planetarium. My name is Shiloh, and I welcome you to our third in our lecture series on exoplanets. And I'm going to go ahead and bring her up and let her do her thing. So thank you.
Hi, everyone. Can you hear me?
Yes.
Hi, thanks for coming out tonight. I'm really excited to be here. My name is Schatz, and I just finished my third year at the Ph.D. program at Optical Sciences. My research focuses on developing technologies towards being able to image exoplanets. And so tonight I'm here to talk about the role of optics in exoplaneting and what we've been up to at University of Arizona. So this is a picture of Earth. Right now, it's the only planet possible to sustain life that we know in the universe. From this close, we can see a lot of the features that we associate with sustainability for life. We can see the ocean, we can see plant life, we can see land, we can see weather, and we can see atmosphere. This is another image of Earth. This was taken by the NASA Cassini spacecraft. Up in the left-hand corner, you can see a picture of Saturn backlit by the sun, and you can also see Earth. Earth in this picture is just a little blue dot. And so this is a great exoplanet analog because all we are seeing when we image exoplanets are tiny little dots. So from this far away, even in our own solar system, it's really hard to tell whether or not Earth can sustain life. So then we have to ask ourselves, if we're only seeing little dots, how are we going to be able to determine if exoplanets support life? So what astronomers can do is that they can put what's called a spectrograph on top of their image of the planet. And so a spectrograph at its simplest is just a prism that breaks up the light of the planet into its composite spectrum, which is like a rainbow. So each color of the rainbow is a different wavelength. And so the Earth in its atmosphere has a bunch of different elements and molecules. And so these molecules absorb light. And when that happens, we get features called absorption bands, which show up as these dark strips in our rainbow. And so by matching spectrum to calibrated molecules, we can determine what is the components of the atmosphere of Earth or other planets. And so we have actually done this for Earth. This is what's called an Earth-Shine spectrum. So what we've done is we've looked at reflected light off of the moon and taken the spectrum of Earth. And so from this spectrum, we can see lots of components to supporting life here on Earth. So from the Earth-Shine spectrum, we see water, we see carbon dioxide, ozone, and methane. And so all of these are really core components to supporting us on Earth. So these are kind of the things we're looking for in exoplanets when we take the spectrum. We're looking for water and carbon dioxide and organics. So this is a picture of an exoplanet taken here at the University of Arizona. This is the planet Beta Pictoris b. And all we know right now from this picture is that Beta Pictoris b is about the distance to its star as the distance from Saturn to the sun. So what do you guys think? Do you think Beta Pictoris b is habitable? Do you think we can have life on this planet? What do you guys think? No? Yeah, you would be correct. So it turns out Beta Pictoris b is a super Jupiter. So it's about 13 times the size of Jupiter, and it's extremely hot. And so this planet is about as close to a brown dwarf star, is closer to a brown dwarf star than it is close to Earth. And so we have to ask ourselves, if we're going to be imaging exoplanets, how do we determine which exoplanets are actually going to sustain life if all we're seeing is a dot? So what we do as astronomers is we define what's called the habitable zone. So right now there are 3,767 confirmed exoplanets. And so we want to quickly be able to look at the data set and say, okay, which ones have good candidacy to support life and which ones don't? And so we define this zone called the habitable zone, which is the distance from the star where an Earth-like planet, so a planet about the size and the mass of Earth, could sustain liquid water. And so planets that are about Earth size are what we call habitable. And so we're going to be looking for these habitable exoplanets, and we're going to be trying to image them, and that's what my group focuses on. So what we do is we do a technique called direct imaging. And so that's when the planet is completely resolved from the host star. And so what I mean by that is that we have a very distinct picture of the star, and we have a separate picture of the planet. It's really easy to see what's what. So this is a picture of the exoplanet 106906b, and it's right up here in the right-hand corner. And down here on the left is the star. So we say that this planet is directly imaged, but we want to be able to do this for Earth-sized planets. And so Earth-sized planets are usually closer to their stars, so it's a harder problem. So once we're able to actually directly image these planets, then we go in and put on our spectrograph to start looking for signatures of life. So we have some problems when we're trying to directly image Earth-sized exoplanets. And so the three big ones are resolution, contrast, and image quality. So the resolution problem is just being able to get those separate pictures of the star and the planet. So on the left-hand side, on the top, you can see two circles, right? So this is like two stars. So with a large telescope, you're able to resolve both stars. But if you have too small of a telescope, you're not going to be able to resolve both stars, and it just looks like one star or this kind of blurry blob. And so we don't want that. And so two of the other problems are contrast and atmospheric turbulence. So the contrast problem is that stars are extremely brighter compared to their host planets. So stars are about 10 billion times brighter than their planet. Put another way, if you're getting 1 photon of light from your planet, you're getting 10 billion from your star. So the star signal really swamps out your exoplanet signal, so it's really hard to see. And this is a picture taken by NASA's Space Telescope of a really bright star, and I put in a little red circle to show kind of the region within where we're actually trying to see planets. So it's a really bright area. And so the other problem is the problem of atmospheric turbulence. From the ground, we're looking through multiple layers of Earth's atmosphere. Each atmospheric layer has different temperatures, and those temperature gradients cause turbulence. So if you've ever been outside on a hot day, which is probably really common in Tucson, you can see the kind of wavy effect on top of the asphalt that kind of blurs and warps what you're seeing. And so that's the same exact effect that's happening in the atmosphere. What that is doing is it's taking our starlight and it's blurring it. So there's two problems. So we're blurring it, so that means we're not getting as good resolution, so we're not seeing the details, we're not separately resolving the planet from the star. So we want to solve first the resolution problem. And so how we want to do that is by building really large telescopes. And so the University of Arizona has been a key player in developing really large telescopes because exoplanet imaging is a technology-driven field. So right now we are involved with this project called the Giant Magellan Telescope Project. Within the next 10 years, these giant segment and mirror telescopes are going to be coming online. And so these telescopes have primary mirrors of 25 to 40 meters in diameter. To put that into perspective, the dome that we're sitting in today has a diameter of 15 meters. So we're talking telescope primary mirrors about twice as big as the dome that we're sitting in today. So these things are massive. And so at the University of Arizona, we've been interested in massive telescopes right from the get-go. In 1916, Andrew Elcott Douglas, who was the first founder of STEWARD Observatory, the first dean, he wanted to build our first telescope dome and build the first telescope. And so he was looking for funds, and he had a student named Clara Fish. And Clara Fish was the first person to actually enroll at the University of Arizona when it opened. She was the first woman to graduate from the University of Arizona and the only woman of her class to graduate. So she was taking astronomy under Douglas and knew that he was looking for funds. And she had a friend named Lavinia Steward who was very wealthy. The Stewards made their money through oat milling, and their oatmeal was actually bought by Quaker Oats. So Clara approached Lavinia, and Lavinia, who was an amateur astronomer and was interested in astronomy, decided to donate $60,000 to the University of Arizona. And so they built the first huge telescope here, which was about 36 inches, so about the size of a pizza. So not that big compared to today's telescopes, but big back then. And it also built the STEWARD dome, and the STEWARD dome is actually here today. It still stands. So these are some historical pictures of the STEWARD dome and the first telescope here on campus. On the left is the STEWARD dome. It's right across the street. You can still go in it. It still has a telescope, but the 36-inch reflector has been moved up to Kitt Peak Observatory. In the middle and on the right, you can see historical photos of the telescope being built in the factory of Warner and Swasey. So Warner and Swasey got the contract to build the 36-inch reflector in 1916. But soon after, World War I started, and they had to start making things for the military. So the contract of the telescope actually got pushed back, and it wasn't until 1922 that our first telescope was installed here at the University of Arizona. So at the University of Arizona, we've also been researching how to build these large telescopes, because we can't just start at a 36-inch and move to a 25-meter in diameter telescope. So in 1980, Roger Angell founded the STEWARD Mirror Lab and began experimenting with the honeycomb design and borosilicate glass, which is like Pyrex that you use for cooking. And so the first mirror cast at the University of Arizona was a 1.8-meter telescope that ended up becoming the Vatican telescope on Mount Graham, about 3 hours away. And now we are casting up to 8.4 meters in diameter. And so this is a picture of the Vatican telescope. On the left, you can see Dr. Roger Angell standing next to it. And you can see all these different cells in the telescope. And so these cells are the hexagonal honeycomb design. And so what they do is, before they start casting the mirror, they put in these hexagonal blocks, and then they put in all the glass around it. And so when they heat it up, all the glass molds around these blocks. And then once the mirror is cooled, they remove all the blocks. And so what you get is a lighter telescope that has a bunch of holes in it, but is still structurally stable. And so this is some pictures of the casting of the Large Binocular Telescope, which is another telescope in Arizona. It's also on Mount Graham, about 3 hours away. And so on the left, you can see them putting in those hexagonal blocks. And in the middle, they're placing all the glass. And then on the right, this is what a telescope looks like before they put on the aluminum, so that really shiny coating. So this has been ground and polished, and all I need to do is put on the shiny aluminum part. So this is a Large Binocular Telescope today. It's one of the largest telescopes in the world, and we have many researchers here at the University of Arizona who do exoplanet research with this telescope. So the next project for the STEWARD Mirror Lab is the Giant Magellan Telescope. The Giant Magellan Telescope is going to be 24.5 meters in diameter, and it's made up of 7 8.4-meter primary mirrors. So on the left is a 3D rendering of what the Giant Magellan Telescope is going to look like when it's done and installed in Chile. And on the left, my left, you can see them polishing and grinding the mirrors at the STEWARD Mirror Lab. So to recap, we were talking about the 3 problems in direct imaging of exoplanets. And so we just solved our resolution problem. And our resolution was to build giant telescopes. But we still have 2 more problems. We have the contrast problem, which is where stars are significantly brighter than the host planets. And we also have our image quality problem, which is imaging through Earth's atmosphere. So to solve the contrast problem, we're going to use instruments called coronagraphs. At its simplest, a coronagraph is just a black spot that you put on top of your star to block the starlight. So that's kind of like putting down your shade when you're driving your car to get the sun out of your eyes. It's kind of similar to that. But on real instruments, we use coronagraphs that are extremely more complex. So this is an image taken by a coronagraph on the Magellan Adaptive Optics System, which is run by the University of Arizona. And so what this coronagraph does is it carves a dark region around the star, and we call this the high contrast region, and then in this region you can actually see companions and planets. So now we want to go and solve our last problem, which is atmospheric turbulence. And we solve this problem by using adaptive optics systems. So adaptive optics systems, the goal of them is to take in distorted starlight and produce corrected starlight. So the first thing we do is we take the light from the telescope and we read it into a wavefront sensor. What the wavefront sensor essentially does is it tells you what kind of junk the atmosphere is putting onto your starlight. And then a control system tells the deformable mirror how to bend and to change its surface shape to correct the starlight. And then the result is a beautiful high corrected image. And so these deformable mirrors are quite extraordinary. They're about the size of a penny, and they have hundreds to thousands of actuators on the back of them. And so these actuators push and pull the surface of the mirror and actually deform the mirror shape. And so this is a quick data set of the power of adaptive optics. On the left, we have a picture of a star from a 6.5-meter diameter telescope. It's really blurry, it's really faint, you don't know what it is, right? But in the middle is what happens when we turn the adaptive optics system on. And we see that when we have it on that it's not even just a single star, it's a binary star. So we're really getting a gain in resolution, and we're able to start seeing planets in binaries with adaptive optics. So this is a quick video of how adaptive optics works. This is the Gemini telescope. It's an 8-meter telescope. There's one on Mauna Kea in Hawaii, and there's one down in Chile. And so what it's doing now is it's opening the telescope dome, and it's going to start looking at stars. So here comes the starlight. It hits the primary, secondary, and now it goes through a hole in the primary down to the instrument. So this black box is our adaptive optics system. And so we're first going to take a look at what happens if you don't have adaptive optics. So we're just going to read in the starlight and put it on a camera and see what happens. And look at the computer screen. You see a speckly, messy blur. And so these kind of potato chip shapes are kind of what happens to starlight when it goes through the atmosphere. And we don't want potato chips. We want really nice flat discs. So here comes our adaptive mirror correcting those potato chips, and we get these beautiful flat wafers. And this is our corrected starlight. And so suddenly we're seeing a nice, pretty star. So this is another video I have to show you, and this was taken on the 3.5-meter telescope at the Air Force Starfire Optical Range. And so what it's looking at is the Hubble Space Telescope, and they're turning their adaptive optics system on and off. So you're going to be able to see it in high resolution, and you'll be able to see features such as the solar panel. And then when they turn it off, it's going to turn into a blob. So now it's on, and now it's off. On, off. And so the University of Arizona has also been a key player in developing adaptive optics instrumentation, and so that's what my group does. I'm part of the MAGELLAN Adaptive Optics System group, and so we have been developing AO systems, or adaptive optics systems. We started with MagAO, which is the Magellan Adaptive Optics System, which is currently installed on the Magellan Clay Telescope in Chile. It's a 6.5-meter telescope. The principal investigator for this instrument is Dr. Larry Close, who is part of STEWARD Observatory here on campus, and our first light was in 2012, so this instrument has been operating for many years now. So we have 585 actuators on our deformable mirror, and our deformable mirror is actually the secondary mirror of the telescope. So it's a little different from a classical AO system. And so the number of actuators is really important because it's the number of degrees of freedom we're controlling. If we have more actuators, we're getting better corrections. We're running at 1 kilohertz speed, so that means 1,000 times per second we're applying corrections to the starlight. We have two different cameras on MagAO. We have the Clio near-infrared camera, so if you've ever walked in front of those infrared camera lights and you've seen yourself in kind of different glowing colors, it's the same wavelength bands that we're imaging on Clio. And then we also have VisAO, which is the visible light camera, which looks at the same light that our eye sees. And so this is a picture of the telescope inside the dome, and then this is a picture of the outside of the telescope. This is the telescope dome. And on the left here, this is MagAO strapped to the side of the Magellan telescope. And so the next step that we're developing is MagAO-X. So MagAO-X is an extreme adaptive optics system for the Magellan telescope. And so our goal with MagAO-X is that we're really trying to go after planets. This whole system has been optimized to try to image planets. And so the PI for this project, the principal investigator, is Dr. Jared Males, who's here today. So if you want to ask him questions, you can go attack him, I guess. And he is part of STEWARD Observatory. Our first light plan for this instrument is later this year in winter, and we're using a 2000 actuator deformable mirror, so we're really getting high corrections to our starlight. And we're going to be running at 3 kilohertz speed. So this is a picture of MagAX as it is today. It's being built right across the street at STEWARD Observatory, and soon we'll be finished with alignment and we'll be shipping it to Chile. And so the future of adaptive optics at University of Arizona is the giant MAGELLAN telescope extreme adaptive optics system. So this is called GMAGAX. So the idea is that we want to put an adaptive optics system capable of imaging exoplanets on that 25-meter giant MAGELLAN telescope. So how we're going to do this is we're going to essentially copy and paste 7 versions of MagAX onto the giant MAGELLAN telescope. And so the giant MAGELLAN telescope has 7 primary mirrors. And what we're going to do is we're going to take a prism to split up all 7 mirrors so that we can place deformable mirrors on all of them. And I want to give some special thanks tonight. Dr. Tom Fleming and Dr. John Hill gave me a lot of the history and pictures I was able to share with you today about STEWARD Observatory and the STEWARD Mirrored Lab. And I want to thank my 2 advisors for coming out here and supporting me, Dr. Michael Hart and Dr. Jared Males. And I want to thank everyone in my research group. And that's all. Thank you.